Hello, ladies and gentlemen. This is the introductory presentation for our work, power, and efficiency unit, and we're going to be talking about the physics definition of the concept of work. So, work in physics is the transfer of energy. It's a measure of the transfer of energy. So, as we go through this presentation, please take Cornell notes on the Cornell note sheet that's provided to you. Work is also a vector quantity, so direction matters when we're dealing with work. So work can be done by you if you make the force, or work can be done on you if there's a force that does something to you. So the important idea here is that work is a vector quantity. It has a direction. The other important thing about work is that there's some specific rules that need to be met in order to use the equation you see on your screen. The simple form of this equation is work equals force times displacement. And the force and the displacement need to be parallel. So for more about that, to use that work formula, work can only be done if the force that you put in the equation is the one that causes the object to move. And the other piece of that is that work is only done if components of the force are parallel to the displacement. So that means that the object moves because of the particular force you're using. You'll see a little bit more about those ideas in just a moment. But we have to be cautious to make sure that the force we use in the work formula is the one that causes the displacement, and that we actually have motion due to that force. Okay, the units for work are joule, J-O-U-L-E. Mr. Joule was a British scientist, and so they named the unit joule after him. If you look at the unit analysis for it, work again equals force times distance, and a joule, which is what we measure work in, is equal to a Newton meter. A joule is considered a derived unit since it's a nickname for Newton meter. The abbreviation for a joule is an uppercase J, and the abbreviation for work is an uppercase W. So the correct way to write a work equation is like you see right here on the screen. W equals some number, in this case 45.6 joules. Okay, let's think about simple machines. You all know a lot about simple machines. And the basic idea of simple machines is to make it easier to do work. So let's kind of see how we can do work more easily using a ramp or an incline plane. First, let's see what it would take to lift this crate without a ramp. So we're going to lift a 3-kilogram crate straight up 1 meter, and we want to calculate what the lifting force is. So if the crate equals, if the mass of the crate is 3 kilograms, then there's going to have to be a lifting force that is equal to or greater than its weight. So we need to calculate what that weight will be in order to figure out what our force needs to be in this case. So the weight of the crate will be 3 kilograms times 9.8 meters per second per second. So the weight of the crate is approximately 29.4 newtons. Now, if we lift the crate straight up, so the distance moved is 1 meter, then we can use this work formula and drop 29.4 in for the force and 1 meter for the distance, and find that it takes 29.4 joules of work to lift this crate directly upward. Now let's compare that to how much work it we would do by using a simple machine, a ramp, and pay in particular attention to how the force and the distance might be affected by that. Okay, so here's our ramp. We have the same mass. We have a 3-kilogram mass that we're going to push all the way up this ramp. The ramp is 10 meters long and 1 meter high. So it's 10 meters along the surface of the ramp, and it raises the object ultimately 1 meters, which is the same thing we did before when we raised the object straight up. So if we extend the force over a 10-meter area, we only have to use 2.9 newtons of force, or about a half a pound of force, in order to push it up this ramp. So we apply only a 2.94 Newton of force, but we apply that force over 10 meters, a long distance, and we do the same amount of work on the crate. So if we look at this comparison side by side, by either lifting this crate or by pushing it up a ramp to the same height, we're going to do the same amount of work on the crate. We're going to transfer the same amount of energy to the crate, in this case, 29.4 joules. The difference, notice there's a big difference here in the forces required. There's a force of 29.4 newtons to lift it straight up, where we only have a force of 2.94 newtons when we use the ramp. And the distance moved was only 1 meter when we lifted it straight up, but it was 10 meters when we used the ramp. That's pretty important information. So how do simple machines make it easier to do work? Well, let's look again at the idea of exerting a smaller force over a larger distance to achieve the same change in gravitational potential energy or achieve the same height raised. So ramps allow us to use a smaller force over a longer distance. That's one of the things you'll need to record on your notes page. The summary at the bottom asks you to summarize this idea. So if you need to stop here and do that, feel free. But try to put it in your own words and pay attention to the larger force, shorter distance, smaller force, longer distance. But the advantage of a simple machine like a ramp is that we can do the same amount of work on the object. Okay, I'm going to pause here. I'm not going to click this and go to this YouTube video. I want you to maybe stop this video now and open the YouTube video that you can get to on our website. It's posted out there right beneath this video. And watch that Eureka video. It's a good idea to stop this, just minimize this and open the other one and watch the Eureka video and then come back and finish this. There's a question on your notes page at the top of the back of the sheet about that Eureka video. So go ahead and watch it. It's cute and it's short. And then come back to this. Okay, I guess you're back. We're going to do a couple of problems now. If a man applies 600 newtons of force on a boulder, yet the boulder does not move, how much work does the man do? When you watched the video, the Eureka video, you learned some information that helps you solve this. We have 600 newtons of applied force on the boulder, but the boulder doesn't go anywhere. So the distance moved is 0 meters. We can take that information and we can put it into the work equation, and we find out that the force of 600 newtons times a distance of 0 means that we do 0 joules of work on that boulder since it doesn't move. And that was part of the idea of that I wanted you to pull out of the video, that if a force is applied to an object but the object does not move, then no work is done on that object. Okay, so how much work is done on something when you push on it and it doesn't move? No work. No work is done, so work is equal to 0 joules when no motion results from the force applied. Okay, now, one of the things you have to be careful about whenever you're doing work equations is to make sure that the force that you use in the calculation is the force that causes the motion you see, because objects can have lots of forces acting on them. So in this case, we want to answer the question on the screen. How much work is done by the applied force if the file cabinet moves 3 meters to the right? Well, we have lots and lots of forces acting on this. We have an applied force of 7 newtons. We have a friction force of 7 newtons in the opposite direction. So we know that since this is moving across here, since these forces are balanced, then it's going to move at a constant velocity. We also know that we have a weight of 45 newtons, a force due to gravity of 45 newtons, and it's resting on the floor, so the floor is pushing back with a normal force of 45 newtons. Well, we need to use only the force that causes this to move. So if it moves to the right, if this thing moves this way, then it's going to be the applied force right here that causes that motion. Now that might seem really simple, but that's a really, really common mistake made in making force calculations, is choosing the wrong force to put into the work calculation. So let's go ahead and finish that. So how much work is done by the applied force? Now this question kind of helped you with that. It pointed you to this as the applied force. If the cabinet moves 3 meters to the right, we may have a force due to gravity on this, but if this moves 3 meters to the right, then we are going to use the 7 newtons in our calculation to answer this question. So the work done on this will be 21 joules of work. 21 joules of work was done to move the file cabinet 3 meters from left to right. Now, how much work is done by the force due to gravity if the cabinet moves 3 meters to the right? Well, in this case, let's pay attention to this. The motion of the file cabinet is 3 meters to the right. The weight is down. Now remember, one of our rules was that the force has to cause the motion, and the force and the motion have to be parallel. Well, they're not parallel, they're perpendicular, and the weight of the object certainly isn't what makes it move side to side. So in this case, the force due to gravity, the weight of the object, does 0 work on the file cabinet. Okay, now let's kind of generalize that idea, and let's pay attention to this case. We always have to make sure that the component of the force is parallel to the direction that the object moves. So in this case, we're going to have to look at the forces acting on this ball and figure out what's parallel to the direction of motion. So if the beach ball rolls down the ramp, is work done by the force due to gravity? Well, it rolls down, so we have motion. This is what the force diagram looks like for the beach ball. We have a force down, Fg. We have a normal force up, Fn. Well, we need to look for a force that's parallel to the motion, so parallel to the ramp that it moves down. So let's look at how we're going to come up with that force. If we take the weight of the object, which is this kind of grayed out vector, this Fg vector that's straight down right here that my cursor is going over, if we take that and make that the hypotenuse of a triangle and take the components of that vector that go into the ramp and go down the ramp, then the component of the weight that's parallel to the motion, or in other words, the component of the weight that's acting down the ramp, that's the part of the weight that could be used to determine the work done. Now, in this case, let's think about this, the snail walking up the ramp, well, the blade of grass, I guess. If the snail crawls up this blade of grass, is work done by the applied force? If he moves this way, and the applied force is that way, then I would say yes, work is done by the applied force. And how much of the applied force is doing the work needed to move up the blade of grass? All of it would be, since the applied force is parallel to the motion up the blade of grass. Okay, quick summary. Work is the transfer of energy. The formula for work is work equals force times distance, and we use that when the force and the distance are parallel, and the force that we put in the equation is the one that causes the motion. And the last piece of information that's new today is that the standard international unit for work is a joule. Now you have some practice work you need to do to kind of make these concepts a little bit firmer in your mind. Good luck. Do your best.